Okay, so in this section, we're going to find the max or mean value of a given quadratic form Q of x on some constrained set. So for simplicity, we will assume that x is a unit vector. So that means the magnitude of x equals to 1, or if you take the square for the both sides, then we have x squared, or the magnitude of x squared equals to 1. And this is equivalent to have x dot x, or x transpose times x equals to 1, or if you expand that, we get sum of squares equals to 1. So let us find the maximum and minimum value of the quadratic form given by 9x1 squared plus 4x2 squared plus 3x3 squared in a constraint x1 squared plus x2 squared plus x3 squared equals to 1. So things that you can observe is, well, we have 9 as the largest coefficient in Q of x. So 9 is the largest coefficient in the Q of x. And also, we have x2 squared and x3 squared is all positive because they are squares. So that gives you 4x2 squared is less than or equals to 9x2 squared, and 3x3 squared is less than or equals to 9x3 squared. With these observations, we can tell that our quadratic form Q of x, which was given by 9x1 squared plus 4x2 squared plus 3x3 squared, should be less than or equals to 9x1 squared plus 9x2 squared plus 9x3 squared. Or if you factor out by 9, then this gives you 9 times x1 squared plus x2 squared plus x3 squared. But we have the constraint that the sum of squares, x1 plus x2 squared plus x3 squared, equals to 1. So this gives you, this should be 9. So what we get is Q of x is less than or equals to 9 for all x a unit vector. So basically, we proved that Q of x is less than or equals to 9, but we want to show that the max value is exactly 9. So basically, we have the fact that, so if you plug in x equals to 1, 0, 0, then this is a unit vector. So if you calculate Q of 1, 0, and 0, then this gives you just 9. So combining with this and that, we can tell that the quadratic form Q attains maximum value 9 at x equals to 1, 0, 0. And similarly, the smallest one among all the coefficient is 3. So the smallest coefficient is 3. So you can tell that. So you will get the minimum value equals to 3. And this occurs at the vector 0, 0, 1. So you want to check this by yourself. So if you summarize the result above, then we get the maximum Q value 9 at the vector x equals to 1, 0, 0, and you get minimum Q value 3 at 0, 0, 1. So what does those max and mean value mean? So basically, how do 9 and 3 and actually 4 related to Q? So basically, we had Q of x equals to 9x1 squared plus 4x2 squared plus 3x3 squared. So A should be, I guess, 9, 4, and 3, and there are no cross product terms. So we get the diagonal matrix. And you can tell that the eigenvalues of A equals to lambda is 9 and 4 and 3. So the max value of Q should be the largest eigenvalue of A. And on the other hand, the minimum value of Q is the smallest eigenvalue. when you write Q as the matrix vector product. So this theorem summarizes the previous observation that we had. So if A is a symmetric matrix, and suppose that M is the minimum value for the quadratic form defined by the matrix A, constrained in the unit vector, and M be the max value constrained in the unit vector as well, then small m corresponds to the smallest eigenvalue of A, and the large M corresponds to the largest eigenvalue of A. And if you plug in the corresponding unit eigenvectors, then Q of U1 equals to the minimum value, and Q of U2 equals to the maximum value. So let us see what those max and min value mean in geometry. So let's say A is given by 4, 0, 0, and 5, where Q of x is defined by x transpose A times x, and this certainly equals to 4x1 squared plus 5x2 squared. So if you plot Q of x in 3D, then you will get the hyperboloid that is given by, so the z-axis is Q, and we have x1 and x2 here. And if you cut out this paraboloid by the unit cylinder, or the cylinder of radius 1, then you will get a cross-section that looks like this. So this purple thing is a curve on Q, that is the cross-section of the constraint. Or if you take off that curve and copy that over here, then we have something like this. Then we have minimum values over here and maximum values over here. So we know that the eigenvalues of A equals to, well, because that is diagonal, we have lambda 1 is 4 and lambda 2 is 5. And the corresponding eigenvector should be U1 is just 1, 0, and U2 is 0, 1. So if you plug in Q of U1, which is given by 1, 0, then you will get, I guess, 4 times 1 plus 0 is 4. And the Q of negative 1, 0 is again equals to 4. And Q of 0, 1 gives you, I guess, 5. And Q of 0 and negative 1 equals to 5. So we can tell that this point that is in direction of positive x1 axis is given by 1, 0, and 4. And the other minimum point is given by negative 1, 0, and 4. And the maximum value is given by 0, 1, and 5. And the other maximum value is given by 0, negative 1, and 5. So geometrically, the solution to the constraint problem corresponds to the max and min value of the curve, that is the cross-section of the given constraint. Now, suppose that A is given by this 3 by 3 matrix, and let us practice to find max and min value of the quadratic form when x is the unit vector. So let us pause the video and try out the problem before I give you the solution. So did you figure this problem out? So the first thing you want to do is to find the eigenvalues of the given matrix. So the characteristic polynomial is given by this, and the synthetic division gives you that. So this tells you that the eigenvalues are 6 and 3 and 1. So the largest eigenvalue equals to 6. So we can tell that max value should be 6. And we want to find when we get the max value. So we have to find the eigenvector corresponds to the eigenvalue 6. So basically, we need to find the null space of A minus 6i. And this equals to, I guess, negative 3, 2, 1, 2, negative 3, and 1, 1, 1, and negative 2. And this corresponds to the first matrix above. So the RREF of this matrix is given by 1, 0, negative 1, 0, 1, negative 1, 0, 0, 0. So this gives you x1 equals to x3, x2 equals to x3, or the solution set, or the general element for the null space equals to x3, x3, and x3, or this gives you x3 times 1, 1, 1. So if you let 1, 1, 1 equals to v1, then the unit vector in the direction of v1 equals to, so if you normalize v1, then this gives you, well, I guess the magnitude of v1 equals to square root of 3, because 1 squared plus 1 squared plus 1 squared. And you multiply this to v1, that equals to 1, 1, 1. So u1 should be 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3. So the maximum value occurs at u1 that is given by this vector. Okay, so we can do the same thing for the minimum value. So the smallest eigenvalue is given by 1. So we can tell that the minimum value for the quadratic form should be 1. And that happens when you put the unit eigenvector corresponds to 1. So basically we have to find the null space of A minus 1 times I. And this equals to 2, 2, 1, 2, 2, 1, and 1, 1, 3. And if you use the second fact that is given, then this matrix is row equivalent to 1, 1, 3, 0, 0, 1, and 0, 0, 0. And this gives you, well, x3 equals to 0, and x1 equals to negative x2 minus 3x3, but x3 is 0. So the general element of the null space, or the solution set for the homogeneous equation, is given by negative x2, x2, and 0, or you get a corresponding eigenvector as negative 1, 1, and 0. So again, if you let this equals to v2, then the unit eigenvector should be, well, the normalized vector of v2. So you divide v2 by its magnitude, and this equals to 1 over square root of 2 multiplied to negative 1, 1, and 0, or this equals to negative 1 over square root of 2, 1 over square root of 2, and 0. So the minimum value occurs at negative 1 over square root of 2, 1 over square root of 2, and 0.